Hello. In this video, I'd like to cover a few miscellaneous issues that pertain to problems that students have when they analyze these circuits. I covered them with 8 examples here. So I'd like to start out and take a look here at this example number 1. You don't have this in your lecture notes. I have a simple series parallel circuit here, and I want you to take a look at the current I through this 10 ohm resistor up here. A lot of students will go ahead and they'll project this 10 volts, this 100 volts across that 10 ohms, and they'll say that the current there is 10 amps. You cannot take this 100 volts and project it across this resistor here, because there's another part to this circuit here. So the current in this circuit here, total current in this circuit I here is not 100 over 10. It's not 10 amps. Why? Because you have to take the circuit and you have to look at the series combination of the 15 and the 5 to get 20 down here. And you see that that's in parallel with this 20. You have to work toward a total resistance looking from the source here of 100 volts. This 20 in parallel with the 20 on a product over the sum gives you 10 ohms. Now you can take a look at this circuit simplified, and the total resistance looking in from the source is 20 ohms. So the current I is equal to the total voltage divided by the total resistance, which is equal to 100 over 20, in this case, which is 5 amperes. So that current is 5 amperes. Now, once we know that current, we can go back up here and we can calculate the voltage at this point here. Because we know we have 5 amperes flowing through 10 ohms, that gives us a 50 volt drop. So if we're at 100 volts here and we subtract 50 volts, that leaves 50 volts at this point. But we already knew that from down here, because this part of the circuit here can be represented by a 10 ohm resistor. And it's a simple voltage divider rule down here to get that point V1. V1 is equal to the total voltage 100 times 10 divided by 20, and I got 50 volts. So you can see this point V1 is the same point as this V1 up here. Do not take these voltages here and project them across the resistor up here. This 100 volts, if you take a look at the Kirchhoff's voltage law, this 100 volts has to be dropped across this resistor and the combination of these resistors in parallel with this resistor. That's what makes up the 100 volts. Let's take a look at another problem. Problem number 2. Again, in problem number 2, the voltage out here. The voltage out is not 0 volts. Why? Well, if you take a look, no current can flow at this point right here because that's an open circuit. We don't have a resistor there. So that current flowing through this 10 ohm resistor is 0. So the current from this 30 volt source just flows in that loop right there. So if I take 30 volts and I divide it by this resistance right here, I will get the current. The current's 1.5 amperes. I have 1.5 amperes flowing in this loop. If you have 1.5 amps flowing through 10 ohms here, that leaves 15 volts across this resistor. If you have 15 volts at this point and you don't have any voltage drop at this point, your output voltage, V out, has to be equal to 15 volts because there's no voltage drop plus to minus up here. Don't forget that passive convention. But we already knew that. We didn't have to calculate the current because you know that if there's no current flowing out here, you can get the voltage at this point using a voltage divider rule. 30 times 10 divided by 20, or it splits evenly because these resistors are identical. Out of that 30 volts, you have 15 volts there. 2 ways of looking at that. And since there's no current flowing here, you do not get a voltage drop. If you have 15 here, you have to have 15 there. Again, don't take that 30 volts and drop it across that 10 ohms. Doesn't work that way. Let's look at the next problem. Problem number 3. Let's look at the current I1 in this circuit. I labeled current I1 in this direction, I2 in that direction, and I labeled them plus to minus, plus to minus. Don't forget the passive sign convention. It's very important. The current I1 in this circuit is not equal to 50 over 25. Again, don't take the 50 and project it over here. There's another part to the circuit. You can't do that. The current I2 here in this circuit is 2 amps. There's only one current that we know by inspection looking at this circuit without doing an analysis. We know that the current from this point here up through to this point is 2 amperes. Because that's a series section of the circuit, and I'm telling you that branch current is 2 amps. So the only voltage we know here, we know 2 voltages in this circuit. We know this point here with respect to ground is 50 volts. The voltage at this point is 50 volts with respect to ground. And we know if the current flows in this direction, which it does in this independent current source, the voltage has to be plus to minus, and you have 2 amps flowing through 15 ohms. That gives you 30 volts. So we know the voltage across the 15 ohm resistor is 30 volts minus to plus, minus to plus. Look at example number 4. I want you to take a look and tell me what the current IX is. If I show IX in this direction, well, we have to put the passive sign convention in, plus to minus, in the direction current is flowing. Do you see that the current IX through that R3 resistor there is equal to the voltage on this side, because it's the plus side, minus the voltage on this side, because it's the minus side, divided by R3. We can further take that to say that IX is equal to V1 minus 40 all over R3. Why? Because there's no resistor up here like there was over here. If this is 40 volts at this point with respect to ground right here, that puts this point and V2, they're the same point at 40 volts. So I'm just taking V1 minus the voltage at this side, which is a plus 40, V1 minus 40 over R3. You're not projecting this voltage across the resistance up here. That node voltage is this node voltage. Over here, you can't do that. You can't take the 20 and put it over here. You can't project this 20 across this resistor. You can't project this 20 to that point. That resistor messes you up. Be careful with that. Problem number 5. Let's do the same thing, but let's have current going from right to left. Here's a V1, here's a V2. I call this plus 40. I have current shown in this direction now. I put the passive sign convention in, plus to minus. The voltage V1 at this point isn't 20 volts. You can't project that up there. We've talked about that numerous times now. This voltage, if you go around the loop here, this 20 volts is a rise, and you have a drop between this point and this point to get to 20. So you can't take all 20 of that across that resistor. The only thing you can say in this loop here is this 20 has to be equal to the voltage across this plus the voltage across that. The rise has to equal the drop here and the drop there. That's all you can say. What about V2 though? V2 you can say is equal to 40 volts because this point here and that point and this point are all the same point. What's IX in this problem? Well, look at the direction of current. The direction of current goes this way. Current always goes from plus to negative. Look at this. There's a positive. There's a negative side. You put them in. So the current is V2 minus V1 all over R3. And we can take that to say, what's V2? Well, we know V2 is 40 minus V1 all over R3. So there's the final value for IX in this example. It's 40 minus V1 over R3. The voltage here, which is 40, minus V1 divided by R3. What's I1? What would I1 be in this? Well, I1 would simply equal to voltage, put the direction of current in, it's plus to minus. It's V1 minus 0 all over this resistor here. Let's call it R4. That would be I1, V1 over R4. What's I5 going to be? We call this I5 here, that I2 here. We labeled it I1 and I2, so we called that I1. Let's call this I2. Already have it labeled, plus to minus. It's V2 minus 0 over R4. And we know V2 is 40 volts. It's just whatever 40 is, 40 volts over whatever R4 is. That's what I2 would be in that problem. I2 is V2 minus 0 over R4. And we know V2 was 40 volts by inspection. 40 over R4 over R4. What about problem number 6 down here? Let's take a look at it. I want you to tell me what V1 is in this circuit. This node voltage right here in this circuit. It's not 20. If you take a look at this circuit here, by inspection, you can't tell me what that node voltage is. You cannot tell me by inspection what that is without analyzing the circuit. What about V2 at this point? Well, V2 is a minus 40 volts. You can do that by inspection. I turned this upside down here. V2 is a minus 40. So what's Ix going to be in this problem? What's the equation for the current? Can you write it? Look at the direction. It's a V1 minus a minus 40 all over R3. That turns out to be equal to V1 plus 40 all over R3. Take a look at that. You distribute that minus sign on the negative 40 here because this is turned around. So the value, the equation for that current Ix there is going to be V1 plus 40 over R3. How about problem number 7 here? Let's look at problem number 7. Can you tell me what by inspection, can you tell me what I5 ohm is? What's I 5 ohm in that circuit? Stop the video and look at it and tell me if you can figure it out. Well, it's the voltage. Look at the direction of current, plus to minus. It's 15 minus, what's the voltage on this side? It's 15 divided by 5 ohms. There's no amperes flowing through that resistor because there's no potential difference. You have 15 on this side and 15 on that side. How about the current in the 15 ohm resistor? The current here. Well, if you take a look at this circuit here, you have 15 volts across 15 ohms. Do you see that? This is telling you that there's 15 volts across that 15 ohms. This has no effect on that. So, 15 volts across 15 ohms is 1 ampere. The current through the 15 ohm resistor is 1 amp. Remember on a problem back here, we had this. Let's see if I can find the problem here where we had that current source. Yeah, remember this current source right here where I said, you know what? When you have an independent current source in a branch, current flows That current flows in that branch independent of anything else in the circuit. That's an independent current source. Nothing else is going to influence the current. So you know you have 2 amps flowing through that 15 ohm resistor because of that. Well, that's the sort of the same thing we're doing right here. Except with a voltage source. This is an independent voltage source. That means that it is independent of anything else in the circuit. There's 15 volts from this point to this point, independent of anything else. Now, if these were dependent voltage sources, and if this turned out to be a dependent current source, that would be different, but they're not. They're both symbols for independent sources. So that's why we can make this calculation. And then finally, let's take a look at this, problem number 8. Here's my circuit. What is the voltage at node A? Look at this circuit and tell me, can you tell me what the voltage at node A is? You cannot project this. Some of you are going to do this. I could tell you this 50 times. Some of you are going to try to project these voltages. I've been seeing this for 30 years. Don't do that. You can't take this 20 volts and you can't put it up here. Can't do that. That 20 volts is go around the loop. The only thing you can say here, the way I have things labeled here, is this 20 plus 20 minus Vx minus Va has to equal 0. This 20, this rise has to be dropped here and dropped here. So you can't take 20 volts and just put it there. The answer is you can't, by inspection, find what Va is. You can't in this circuit. You have to analyze the circuit. The first thing I want you to notice here by looking at that circuit is we have a voltage-controlled voltage source here. That is your controlling variable. It's V sub x. What is V sub x? Looking at this problem right here. Well, you can see it's the current here times that 1K resistor. We could define V sub x in terms of the current. It's Ohm's law, current times 1K. So it's I1 times 1K. That's what V sub x is. But I want to find, in this equation here, I want to define VA in terms of the 20 volts in the Vx. Do you see, if you're at 20 volts, this is your reference point. If you're at 20 volts here, and you come down Vx, because I define Vx here, plus the minus, you're at VA. So if I have 20, and I subtract Vx, I get that voltage VA. That's the relationship between this and this point. So what is VA? VA is 20 minus Vx. This point here, VA, an equation for that is you're at 20 volts there and you subtract Vx, you get VA. And then I look at node V1 by Kirchhoff's current law. I look at that node, VA right here, by Kirchhoff's current law. And I labeled the current coming in here as I1, the current coming in here is I2, and the current going down here is I3. I put my sign convention on, my passive sign convention. You have to put passive sign convention on these, or you're going to be messing up your equations, your nodal analysis and your loop analysis that's going to be coming up. So I say at node V1, see if you can't get all this on here, at node V1, in this case it's not node V1, it's going to be node VA. At node VA up here, by Kirchhoff's current law, my first level equation is a plus I1 plus I2 minus I3, because it's leaving the node, has to equal 0. Well, what is Vx? Or what is I1 here? What is the current I1? Well, it's Vx divided by 1K. That's what I1 is. It's the voltage across here divided by 1K. What is I2? What's the current I2 up here? It's the voltage at this point minus the voltage at this point divided by 2K. So it's a plus 5 Vx minus Va over 2K. It's the voltage at this point minus the voltage at this point divided by 2K. Just Ohm's law. And what's I3? I3 is just Va over 10K. Well, it's really Va minus 0 over 10K. But there's VA over 10K equals 0. Well, there's one equation with two unknowns, but we know what VA is equal to in terms of VX. VA is equal to 20 minus VX. So I'm just going to substitute that in here for VA and here for VA. And I did that. Don't forget these parentheses. Don't forget those parentheses in your algebra. If you forget those parentheses, you'll forget to distribute this minus sign on that minus sign, and you'll forget to distribute that minus sign on that minus sign. You just clean this up. You get a least common denominator here of these three terms is 10K. You multiply everything through by 10K here, and you solve for VX. Once you find VX, you can come up here, and if you know VX, you can get your answer for VA. Not a bad problem to work out. You should probably work it out. But you cannot look at that circuit and by inspection and tell me what VA is without going through this analysis. And I hope that these techniques that I showed you here in these 8 problems, it's nothing new. The other videos cover it, but I noticed that students have problems, have issues, and I wanted to resolve some of those analytical issues by going over these 8 problems. And that concludes this lecture.